everyone. I hope everyone's having a fine day and welcome again to another episode of the Focus on Geothermal webinar series. This is a partnership between Enerchange and ThinkGeo Energy. And again, I'm Carlo Cariaga from ThinkGeo Energy. And today we're talking about sedimentary geothermal, specifically the challenges faced in exploiting or utilizing sedimentary geothermal reservoirs when it comes to productivity and permeability. And today we are featuring Maren from the ETH Zurich in Switzerland, who will be presenting her studies on sedimentary geothermal reservoirs and results of studies on chemical stimulation. Maren is a hydrogeologist from the Geothermal Energy and Geofluids group of ETH Zurich, with research that aims to understand subsurface fluid flow using multidisciplinary approaches for sustainable geothermal exploration and exploitation strategies, with a strong focus on fieldwork and real-scale data. Maren's main research objective is finding new well locations during geothermal exploration and field development and on optimizing sustainable geothermal energy extraction and conversion. For the audience, feel free to type in your questions. There should be a questions tab in your webinar panel, and we'll get to those questions after the presentation. Maren, the floor is yours.
Yeah, thank you very much, Carlo, for the invitation, and welcome also to everyone from my side. I'm happy to be here today. Yeah, let's talk about sedimentary geothermal reservoirs. I'll present about our field experience, case studies, but also a little bit kind of outlook in general. So when we compare these systems, how do they look like actually? Normally it's a very basic setup, a simple geology-wise at least to understand. Normally they are horizontally layered sedimentary lithologies like sandstone, might be marble, something else in between, and there's a basement below. There might be some faults where fluids move up or also down, and there's some heat flow from beneath. So the geology-wise, pretty simple to understand in the first place. There was a study by Breheme, and he understood the already identified sedimentary geothermal systems worldwide, here labeled in green on the map, and then also potential areas that are not in use yet. This is focused on the very applied side. When we look into the IFC report regarding drilling success in geothermal, we see that sedimentary systems have the highest drilling success by nearly 90%. So it's due to the geology, I think, that we basically understand these systems and know where to drill. The fluids can easily move in these sedimentary layers because there's high porosity and high permeability. If we look into the geology worldwide on the left side, we see there are many more places we could explore actually. So there are a lot of sedimentary basins worldwide, here marked in green. So every continent has actually the potential for using these sedimentary geothermal systems. On the right side, there's a world map showing the geothermal heating and cooling, which is already installed globally. You see nearly every continent here is involved, and the potential, the already installed capacity is of course quite different. There are many reasons for that. We won't touch that topic. What I'm saying is that these sedimentary geothermal systems are mainly used for heating and cooling. That's why I put this map also here on that slide to compare how much potential actually you have geology-wise and how much actually is already installed. So I think there's a huge potential still to be tapped in these reservoirs. Compared to other systems like volcanic regions, of course, the temperatures in these systems are lower. Though we have the advantage of already understanding these systems pretty well because of oil and gas industry. Oil and gas reservoirs also occur in these sedimentary setups. So there has been a lot of research, but also, of course, industry activity in these systems. So we understand these systems quite well. Even some of the fields which are explored for oil and gas might nowadays be used for geothermal. There are also ideas like that. And as I said, the porosities and permeabilities are normally pretty high. So we have good fluid flow in these systems. I put here two case examples, one from Lithuania and one from Hungary, which I will cover today. And we will look into the challenges, but also the opportunities. So first of all, let's look into the case studies regarding the challenges. I will present to you two case studies, as I just said, from Lithuania and Hungary, which cover pretty much what is experienced or what can be experienced in these geothermal sedimentary reservoirs, and these are quite typical examples. So this Klaipėda site in Lithuania, on the very west coast of Lithuania, built a geothermal power plant, a heating plant, and they drilled actually 4 wells. Though only 3 were in use in the end, you will understand later on why. They produced like 100 cubic meters per hour to inject again back to the reservoir using 2 different wells. It's a simple geological setup, as I said, horizontally layered sediments. And I also put the QR codes here, the 2 publications I'm referring to. I'm showing that at the end again. This is just a picture of the power plant. So unfortunately, this power plant experienced some severe injectivity drop. You see here the 2 curves interrupted even over the years. So this power plant got into use in 2002. And after first well cleaning, 2002, the injectivities were pretty high, very reasonable injectivities, very good future outlook actually for this power plant. But then you see the first mark here, gypsum precipitation. So they had really severe precipitation along the whole surface pipelines, the heat exchanger, but also down into the well bores. And I really saw this huge gypsum precipitation around the ESP, around the pump. So after that, they had to somehow reinstall the surface pipeline. They had to clean the wells. They had to deinstall the pumps and clean the wells and all the whole system. And you see in the curves that actually the injectivity never picked up again to the initial level. It always dropped down, and at one point it stayed quite low, although they tried quite a lot. And you see the list here, what they tried to clean and to bring back the injectivity. They even drilled a sidetrack. They used different drilling technologies even to drill laterals from that well, and they still could not recover this injectivity. And this is just one example, but and a quite severe example, but we see this injectivity drop quite a lot at power plants. So these are as a picture of the gypsum precipitation, what they have in their hallway in the power plant. And on the top, you see a picture of a water sample that we took, and we just kept it closed in the lab, in the fridge. And even after 1 year, without touching it, without any contact to oxygen, we saw this small gypsum precipitation happening here. So on the left side, you see now a kind of circle, I call it the vicious circle, from these challenges they faced, the problems they had to face. So after this precipitation happened, they acidified the wells, but also part of the reservoir, and we put this acidification into our hydrogeochemical model using Freak-C. And we saw when the water, which is in equilibrium with the reservoir rock, of course, is treated by HCl, which they use to acidify and to clean the system, some of the minerals that might precipitate anyway even have increased saturation indices. So this treatment by HCl, this acidification, might trigger more precipitation even. So before doing that, we should consider that and check if we are safe with using that acidification solution. We also looked into filter residuals. You see on the left side these filter bags. There are several of these filter bags in this big tank, basically, and the water is flushing through these filters. We emptied the filters, and this material we found, you see in the pictures, basically 2 components. We have sand particles from the reservoir, which is basically the reservoir rock, the matrix being washed out here, and we also found magnetic corrosion material. On the very right picture, you see it's magnetic. So on top of that, we also checked the not only the filter residual composition, but also the particles in the water before and after the filter. So here you see 4 pictures. The smaller ones are always before the filter, which is installed at the injection well, and the bigger figures are after the filter, so after the water, which is then injected into the reservoir, is filtered. And we see that you see that the orange bar marks the filter, which has a mesh size of 1 micron. Before the water is filtered, actually, there are larger particles, like up to 140 micron on the left side, and the other injection well up to 40 micron. And these actually should all be filtered out once the water passes the filter. But then if you look into the bigger sketches there, you see there are still bigger particles than 1 micron. So this filter system obviously does not work well. And we see that these bigger particles are flushed into the reservoir. The main problem here in this case is that we also analyzed the porosity of the system, that 85% of the pores in the reservoir rock have a size of 3 to 40 micron. And the particles injected have exactly the similar size. So it's a perfect fit of the particles injected into our pores that we actually need and want for fluid flow. So it's a complete block of the system at that time. After they realized this problem of fines migration because of acidification, they released particles from the reservoir, and the filters also obviously didn't work well. They started using inhibitor to stop the precipitation of gypsum, and this worked very well. From then on, they never had gypsum precipitation again. But what they then experienced is an increase in microbial activity. So overall, over the years of using this power plant, the cell counts on production side and also on the injection side increased. And you see the numbers in the very top table. Then we also checked again the filters, which you see here as a sketch. So the water is flushing from the top and then leaving the filter horizontally to the outside. You see that the DOC, the dissolved organic carbon, is also increasing from before the filter to after the filter again. So this filter is also releasing organic material. And then we put one slice of this filter into a tank and let that rotate for roughly a week. Very simple setup of experiment. And we measured the DOC again just to prove our observation at the whole filter size. And again, we saw an increase from 2.2 to 4 in the organic carbon, dissolved organic carbon. So when looking at that, we can only assume that this release of organic material from the filters and also the inhibitor, I can tell you, I don't have the exact composition, like all of us struggle with that. We don't know that from industry, but it's phosphonase based. And the microbiology love that, so we are basically feeding the system. So we are inhibiting precipitation, we're inhibiting precipitation of gypsum minerals very well, but the filters and also the inhibitor cause an increase of microbial activity over time, and also along the production line. So the counts you see at the top table from injection to production site is quite different. So this is another problem we experienced here at that site, and also microbial activity in general is a very common problem in these sedimentary systems. You see a small picture here down within the circle below the biofilm marker. This is a filtered water, and a filter from filtered water, and you see this slimy brown material, which is organic material. So it's a bit stinky and slimy. So there's quite some microbial activity going on here, and this is caused by the inhibitor partly. Then in the end, we also looked into a bit more detail into these components that we found in the filter residuals, so the reservoir material, but also the magnetic material, and we could prove that these minerals that we found from the reservoir, so very typical like quartz and dolomite reservoir minerals. How the reservoir is set up, it's clastic sedimentary layers with carbonatic matrix. And then we also found like magnetite and spilononite. These are hints that there's corrosion going on and corrosion materials. So this biofilm and this microbial activity is also a reason for this corrosion. So the microbiology at the bottom, I don't touch here the details which ones we found, but they release H2S. Basically, H2S is acidic and again aggressive against the tubings, the casing, the well bores, and any surface pipelines. So this is a cause for this magnetic filter residual that we find then in the filters. So in summary, this vicious circle happened to them. They weren't aware of that. They were very positive, very engaged people, very nice people to work with, and a bit unfortunate because we came in a bit late to that project and realized all these problems a bit late. At one point, they had to stop the power plant because they could not inject anymore. They could still produce. And if they turn around the well bores, they were able to produce warm water. But because they have to re-inject, they had to stop this power plant. They basically went bankrupt because other competitors could deliver cheaper heat also at that time. And unfortunately, this power plant is out of operation at the moment. But at least the good news for science is that we understood these problems, we have a good overview, we could publish that and hopefully learn from this. The other case study I would like to present is from Breheme in southeastern Hungary in the Pannonian Basin, more specifically in the Békés Basin. Also here we have nearly horizontally layered sedimentary lithology. Again, clastic sediments with a bit of carbonatic matrix. Here the system is a bit more simple. We have one production well and one injection well, and we produce at lower temperature, or yeah, at higher temperatures compared to Klaipeda. I think I didn't say they produce at 40 degrees. Here we produce at up to 82 degrees, and they plan to inject at 50 degrees. And there are up to 9 buildings were planned to be connected to the heating system. They are like public buildings, elderly houses, schools, whatever is in this small town of Breheme was supposed to be heated by this system. And you already understand from my wording, also this power plant is not in place and not in operation at the moment. We came in also after they realized the problem, and we again used a kind of similar approach that we then also put into a more standardized procedure that I will present, and this is also published here in these 2 publications done by Abel Mako. So we realized that the reservoir itself can already be a problem, although we have this well understanding of this pre-knowledge of these sedimentary systems. Locally they can be very different. And we experienced in this case, for example, that we have very thin reservoir layers. And the thin reservoir layers are also dipping, kind of. And you see in this black-gray picture, there are basically two interpretations at the bottom and at the top. If you have these inclined structures, then they can kind of phase out at one point, or they can reach the other well, from production to injection well. There are 2 options basically, and on the left side on the 3D picture you see it's a deltaic environment and you have fluvial structures here, and they are not all connected, and it's very important to place your wells properly to connect the similar layers. Otherwise you won't get a connection, a hydraulic connection between your 2 wells. On top of that, we also realized these layers have a low permeability compared that we are used to. On the right-hand side, you see a depth plot basically of the filtered of the liners of these wells, and they have very different productivities and also not very high productivity. So we go up to maximum 11 liters per minute. On top of that, already at the surface, when we opened the wellhead and the surface infrastructure, had a look at that, we realized there's quite some corrosion going on. Also here, I refer to 2 publications basically done by Abel, a student working with me at that time, and you will see them at the end again. On top of that, of the kind of reservoir problem that we faced is the microbial. So microbial pollution, we call it here, a microbial activity that we face again. So here we have a more detailed analysis of the bacteria and archaea that we found. We found them in the filters, and we also found them in the Bailey sample that we took from the well. And you see two pictures below how that could look like. And also these are magnetic again, which points to corrosion again. We also have mineral precipitation going on, most probably carbonates and iron oxides or iron hydroxides. This is based on XRD analysis we did, but also based on modeling and quite some extensive modeling that Abel did. And you see on the right-hand side what the model and what the XRD interpretation then gave us. And Abel was also able to calculate how long it would take to actually clock the system based on the porosity that we also know of the system. And he calculated quite a long time actually if there's continuous precipitation to clock up the system versus the experienced time. So they clocked up the system in 21 days. So our interpretation here is that not only mineral precipitation is the reason for this clogging of the system, so there must also be microbial activity. And we also realized in this power plant setup that the influence of oxygen and the inflow of oxygen into the system is a quite severe problem. And I think that's also nowadays kind of common knowledge. And we also have to suggest to that system to be close to oxygen, maybe even nitrogen loaded, to keep the pressure high, to keep the oxygen out. So in any case, we did a few calculations on at what temperature, including oxygen, the contact to oxygen of the fluid, and without, what that would mean for the precipitation of certain minerals. And you see that plotted at the bottom, and also in our publications. So in summary, these two case studies, as I said, they're quite severe examples. Although the plant in Hungary is not in operation at the moment, you will see the positive side of that side in a minute. But let's sum up. What are the problems that we normally face? This is for sure mineral precipitation. This can be fines migration. This can be microbial activity, corrosion, the influence of oxygen. And then also regarding the reservoir itself, we can face low permeability locally, at least in some layers. If it's a fluvial setup, it's much more complicated. There might be low permeability layers that you tap and you're not aware of that. There also might be a small extent of this, if of the layers, if they are permeable. This is quite unfortunate. And then also on the regional scale, and you see on the right-hand side how we try to structure our approach and the risk factors, or the risk that we can face, or the reasons for clogging for a system not being able to go into operation, can also be the regional pressure system. And this is, from my experience, faced in Hungary quite some time, that you have hydraulic heads which are quite elevated, so high pressure systems, and injection into these systems is then, difficult. At least you need a lot of pump pressure to get the water down into that pressure system if it already comes towards you, right? So we differentiate between the regional scale, which can be a few 10 kilometers, the reservoir scale, which is a few kilometers, up to the local scale, and the reasons for and the risk factors. You can see here the lists and the approaches and methods we used to understand if this risk factor applied to our site or not. I also brought a list of other sites that were not successful sedimentary systems, like in Germany, some Großschöneberg, also in Hanover, also around Munich. There are some examples where either wells were dry or the chemistry made such a big mess and problems that we cannot use these systems at the moment. And also, I guess in Hungary, without naming any other sites, there are other sites that are not successful. But now let's make a step forward and look into the opportunities. So we go back to the Hungarian side. Within the de-stress project, we were able to actually recover this system. So we're talking about the same system, you know, the problems already, we understood that, we have been publishing this, and all this pre-interpretation has been going on from 2017 to 2020. And beginning of 2021, we could start with the remediation of the problem and with the stimulation, the soft stimulation, how we call it, to not affect the environment, not affect human, and not affect the reservoir in a negative way, but only in a soft positive way, so make the system work again. So we worked in two phases. In the first phase, we first cleaned the system, especially the well. We made the well ready for logging and also pressure tests. We did a thermal stimulation by injecting cold water with different injection tests. And after that, we logged the well again to see our success. And then later on in the year, during May 2021, we had another phase where we then again cleaned the well after it had stand still for a while. We did some injection tests again. Then we did a sonal stimulation by using HCl solution, so it's acid stimulation. After that, cleaned the well again, brought it back to the normal pH, and a final injection test after that. And I will show you our procedure in a bit more detail. So here you see pictures of the well, how it looked before, and then we deinstalled whatever was possible and put a proper wellhead with a blowout preventer also on top of it to be able to inject get in the logging tools. And on the left side you see a list of all the logging that we did, and we don't have time to look in all the details, but if you're interested, they are in the paper or in a report that I can share with you. So after doing that, we saw that the well and also the surface equipment is basically ready and prepared for injection, for logging, and for also stimulation tests. We went into the well, locked it, and checked all the connections and whatsoever. The casing was not damaged. There was nothing observed that worried us. The cement also looked quite good. Hydraulic seals were in place and also working. There was a very slight deformation observed at one overlap flange, but this wasn't a problem for us. The bottom liner, there we have the injection zone, basically was open to flow, so we saw the perforated intervals. And also the gravel pack was found to be in place and also working. So that was good news after installing this new wellhead, that we were basically ready. The well was ready for stimulation and for testing. So the phase 1 thermal stimulation took place in 3 steps, basically. There was a step rate injection test to show the general injectivity, and we measured the skin, came out 18.8, quite high actually. Permeability we could measure, and injectivity in liters per second and bar. You see here the numbers. After that, we did the constant cold water injection as the treatment. So we injected cold water. It was winter time, so it was basically 10 or 11 degrees warm water going into this 80 to 100 degrees warm reservoir. Then after that, we did a constant injection and again to see the efficiency of our treatment. From the numbers, you see that the skin actually was first getting worse and then a bit better again, but basically stayed the same. Permeability also didn't change a lot, and injectivity also no big change, rather a bit worse. So there's a quite high skin that we observed. No major effect of the thermal stimulation was observed, unfortunately. But the good news is that on the right side you see the 2 temperature logs, the blue line and the red line, and the blue bars are the injection horizons. And you see from the red one to the blue one, so the red one was the first one to the blue one, we now were able to see the injection intervals quite clearly. So you see that at the blue bars, there the temperature is going down, so we see that the cold water is going into these layers, and even how much. So we see that there's quite a difference between these layers, and we were able to now decide, okay, we have to stimulate certain intervals a bit more to make it open for our injection. And based on that, we then planned the acid treatment. So the thermal stimulation itself didn't help much with the reservoir, but it helped us a lot to plan the acid treatment. So it was worth doing it anyway, and also not a very low cost solution here. So in phase 2, later that year, you see the weather is improving, a bit more warm in May. It was still COVID time. It was a bit difficult to get to the site, actually. We first, again, cleaned the well by nitrogen lifting. Then we did a short-term injection test to prove the connectivity between the well and the formation. If the slotted liner is still open, we were able to measure injectivity index of 0.08. Then we did a zonal stimulation, and we were using, and pointing to the right here, certain solutions which are all known. So that's a big advantage of our research project, that we could ourselves, together with the companies, define what composition and what mixture of fluids we would like to inject to acidify and to stimulate the reservoir. And this is all public, this is all known. We can share all the data, how much, where, and what is actually pumped down there. Yeah, then you already see an increase in injectivity at that time. We did another lifting here in the lift test to clean the well, to get all the acid out, to bring the pH back to normal, and then a final injection test to prove the increase of injectivity. And we could increase the injectivity here by a factor of 4 to 10. So this acid stimulation actually was a big success. And yeah, as I said, the big advantage also here of this research project is that we have access to all the data. Everything was shared, everything is open access. So we were able to increase the injectivity index, and the skin is removed by this acid stimulation. So this is quite good news. In summary, you see a plot on the right side how we stimulated the different intervals, up to 11 intervals. We had stimulated here the injection pressure, discharge rate, and total discharge, and so on. You can see that in the plot and also see that in our publications. Then, yeah, in summary, the thermal stimulation was only limited by its effect, but it helped us a lot to identify the zones that we had to want to stimulate them by the acid treatment. We realized this damaged zone that we then removed by the soft stimulation. It was environmentally safe, chemically, and thermal stimulation both were defined as a soft stimulation technique. That's how we did it, at least. How did we do that? We used a coiled tubing system, and this was very important to us, to make this decision to go for a coiled tubing system, to have a very precise treatment with a very small amount of chemicals. So we can be very precise and exact where we place the acid to not harm the environment unnecessarily and still be effective in our injection. Yeah, after that we were able to see a higher injectivity. The reservoir is very sensitive, we realized, in case of untreated water injection. That was the case before we came, and in the very first days of operation, they just injected untreated water, and the reservoir is just not taking this, and it's clogging up very fast. So there has to be some surface improvement on the thermal loop system, making it close to oxygen, but also in this treatment of water, filtering of water before injection. But basically, this geothermal system is saved. Although they face a lot of problems, it's saved, it's ready for heat supply. And this is good news. I want to share, before finishing up with a kind of summary, what is important, what are our lessons learned. It might sound simple, but please keep in mind that some leadership is needed in these large-scale projects. We have been doing that in COVID time. So I and Singers from GFZ, we were the project leaders. We were not able to travel to the site. So a support team on site with a reliable and good communication was key. And today in these hybrid times where we don't meet all the time, it's really a good thing to have. Also to overcome language barriers. You see from a meeting here that we have with the on-site team to explain the problems they have. Also take care of administration, make decisions by yourself, but keep administration involved early enough to have clear contracts, to have clear expectations on both sides. Also data sharing for us as scientists is very important. That has to be clear to the companies too, that what they are doing is shared publicly. We were able to obtain a very comprehensive database, also from the site visit, with pictures and whatever, so we could really track what we did and what's going on. And now I hope with sharing this that you can learn from that and other projects can build on this, and I'm very happy to talk about it. Also, country-specific rules are important to consider when people moving in and out and equipment is moving in and out, so plan some backup time for that too. We also had a public campaign going on in the meanwhile with articles in the newspapers, with people in the village talking to the locals, informing that there's big equipment going around, with restoration, with putting trees back on, putting grass back on, so people are kind of not worried that we destroy something here. Other successful projects in sedimentary reservoirs, so we don't always have only problems. We can have problems, but there's a site in Switzerland which is not well known, so I would like to point it out. It is the site of Breheme, near to the city of Basel. This system is running since 1994, and they don't have any severe clogging problems. So this sedimentary system, with a reasonable temperature of 67 degrees and a quite high flow rate of 90 cubics per hour, is working quite well, and they now are about to extend the site. The same for Middenmeer in Netherlands. Also, they are about to extend their site for greenhouse heating. And the Paris Basin, I think, is a very well-known sedimentary reservoir, working quite well. Also in Munich, although there are some cases where there have been wells which are not successful and are dry, it's also a caustic system partly, so they have some challenges here. And other sites are listed down below. So there are systems in Germany tapping sedimentary reservoirs, which are working quite well. So these are the good news for today. So we at ETH, we also care about the sustainability and the long-term life of these plants, of these systems. And we have basically three focus at the moment. So I have a student, Anna. She's working on why, where, and how much scaling actually happens. Another student focuses really a lot on this: how much scaling risk do we have? How much precipitation can we expect? And then maybe some of you heard about the EasyGo program, which is now going permanent. It's all about the efficient and safe operation. If you would like to learn more about that, I'm happy to chat about it, or you might want to Google that. And with that, I'm ending. I thank you for your attention and my team for all the great research we do, all the great team stuff we have going on, the very nice publications. I put them here again. And if you have questions, I'm happy to take them.
And Maren, thank you. Thank you so much for that presentation. This is a very interesting topic, and for the audience, you feel free to send in your questions. We already have a couple coming in. Maybe just to start off the conversation, what made acid treatment, acid stimulation effective in the Breheme site that was different from the Klaipeda site?
Yes, right. Well, I think one of the key game changers was that we were able to understand before where we had to place the acid treatment. And we were exactly going to that depth, to that injection interval, to treat that in a very focused manner compared to Klaipeda. Also in Klaipeda, the lithology is content-wise same. It's a classic reservoir with carbonatic matrix, and we have the same in Breheme. But in Breheme, the rocks are tighter. They are more stable. In Klaipeda, they washed out a lot of reservoir material. And I guess this combination of washing out actually and opening the pores again, but at the same time also losing and releasing the fines of the reservoir, was probably not the best combination.
Based on what happened in Breheme, would you say that doing a thermal stimulation process first is necessary, or does it facilitate chemical stimulation?
It might not be necessary in all cases, but as it is a low-cost option and you can do kind of easy and cheap beforehand, I would always recommend to do it. because we saw this huge effect of understanding which interval actually is active and which is not, to then plan the acid treatment. You could also go and we are thinking about placing a similar amount of acid to all these intervals, which is possible, and then you lose a bit of efficiency in these intervals where you could place a bit more, and you some of the injected acid is somehow lost because this interval is anyway open. So that would be the downside if you don't understand the effectivity of your intervals before. So I would recommend doing that. Yeah.
Yeah, these questions were asked while you were discussing the Klaipeda site. So maybe just this is a question of modeling. So were you able to determine the temperature, the pH at which precipitation formed, and would it have helped to control the, say, the pumping pressure of the well to avoid scaling?
The pumping pressure. Yeah, a good point. We did not look into that, as far as I know. We looked into the effect of temperature and the effect of pH a bit in Albert's publications on the Breheme site, but no, I think I can't say anything regarding these sites, at least. I don't know.
A question on thermal stimulation for the Breheme site. Was there any sort of seismic monitoring done? Were there any activity recorded?
Mm-hmm. Yeah, good point. Very good point. Yes, it actually initially it was planned to set up a seismic monitoring. Before putting that into place, we were together with seismologists in the project looking into the jacking pressure and this the whole reservoir system and the pressure of the system. And in the end, we concluded that it's not necessary because we will not inject under high pressure. We will use a coiled tubing system to place it exactly at the depths we need, but without high pressure, especially far below the jacking pressure. So even jacking this system, we were kind of nearly sure that it's not possible because permeability, actually the natural permeability is so high, and we just have to overcome the skin with that acid treatment that we eventually then also did. So in the end, we did not put up a seismic monitoring system, but depending on where you are and what kind of system you are, if there are maybe fractures in place, if the pressure is high off the system, it's very well thought to put a seismic monitoring. Yes, that's actually needed.
And then, can you comment on the use of organic acids instead of inorganic acids? Say what kind of geology would that work, and also what kind of geology would it be necessary to stimulate with other acids like hydrofluoric acid?
Mm-hmm. Yes, in general, that's of course it's possible. Hydrofluoric acid was used in the Klaipeda site. I mean, regarding environmental safety and also people safety and how to use it on site and transportation even, there's a whole chain of things you have to think about. It's not easy to get it into a country, to get it on site, to being handled on site. It's a whole different story compared to HCl. That's not the major reason we went for HCl, because our system, we did modeling before, and the HCl was very promising in the effect, and now it can also prove to be very promising and effective. But yes, HF is an option. It was used in Klaipeda. They did it. It's manageable. It's doable. It's more for silica precipitation, and if you want to release more, if you have maybe a thicker skin, if you have a more clastic reservoir, not the carbonatic matrix, but more clastic matrix, and you want to really dissolve also the silica, then you might want to go for HF. And that might also be a reason why we have this fines migration in Klaipeda, because they went, I think, even 2 or 3 times this hydrofluoric acid into the system and released really the reservoir material, which is anyway a very loose material. So we had samples from the well, core samples, and if you would get them in hand, you could actually crush it only by hand. So it's a very loose reservoir. And then, yeah, be careful a bit with using HF also in that sense, not only handling it.
Question on microbial activity, because this is something that I also don't understand quite well. So, compared to the process of mineral sedimentation, what is the process that promotes microbial film forming?
So microbes are in place anyway. They are in the reservoir. They live at the boundary of fluid, rock, pores. I'm not a biologist, so excuse me for any wrong wording, but this is how I imagine it. So they are down there and in the reservoir anyway. So if you go down, if you produce the fluid, you will produce also these microbes. And if you inject, you will also affect their living environment. And then they rely on organic material to survive. And they also rely on a certain temperature to survive. And most of them like it between 40 and 80 degrees, which is a very good assumption for sedimentary reservoirs. We have normally these temperatures there. And then if you go into the systems, and then, for example, like in the Klaipeda site, and use these inhibitors, which are organic based, then you're somehow feeding them. And once they are fat, they grow a lot, and they live in communities. They are not single microbes floating around. Also, that is possible, I guess. But as far as I understood, and said that I'm not the expert, but as what I understood from colleagues and discussions on this and reading on this, they live in these communities, and these communities then appear to us like these slimy films. And these slimy films are quite somehow stiff and strong. They're quite connected, so they can block the pores. They can also block the slotted liners, so the filters that you have in your well. And this is how it happens, based on my understanding.
Are there any specific sort of formations or geologies that promote microbial formation?
If they are special formations,
Yeah.
as far as I know, no. I never heard of a correlation between a certain geology and higher microbial activity. As far as I know, it's more based on the temperature, maybe on the pressure, but also on the organic content in the fluid and in the reservoir, what they can live on. I never heard about geology, but correct me if I'm wrong.
On the matter of social acceptance and communications, has there been any struggle or resistance against the concept of acid stimulation? What has your experience been?
Yeah, no, we did not have. So that's also why we choose the wording soft stimulation, to make it very clear that we indeed use kind of dangerous material, but it will be all subsurface, and we explain to the people it will not come to the surface. Whatever comes to the surface is then disposed in a safe way, and we have a safety concept anyway. Also, the site was kind of close to the city, but not in the middle of the city. So no, we did not have problems in accepting this acid stimulation. The people were in both sides, actually, also Lithuania. In general, when I travel worldwide and visit these power plants, people are quite supportive. I never experienced serious resistance, not me personally. Of course, we hear about these activities, but in general, the local people are quite supportive. They have some worries, but if you talk to them, if you explain to them, and this is our experience in these two cases, that people are quite supportive and they feel safe, especially if you inform them early enough and place information, include them, allow them to ask questions, maybe show them to the site. Yeah.
There's a question here on drilling. So, what is the possible contribution of drilling in damaging the formation, thus causing poor permeability in sedimentary formations?
Yes, sure. So the skin, and also in the Klaipeda case, when I showed these injectivity curves, the drop, you see in the very beginning that there was an injectivity increase because of the cleaning of the well and the cleaning of the surrounding of the well. So the drilling activities, especially the drilling fluid, can severely damage the reservoir, at least in the near well bore surrounding. This is what we call the skin, or the filter cake also. And this is a well-known problem, and there are well-known technologies to overcome that and to choose the drilling fluid wisely, first of all, but then also if it happens, and it happens every time, at least a little bit, how to clean it and how to overcome this filter cake again to make it accessible to the well access. It's connected to the reservoir actually. But yes, we shouldn't neglect that this is for sure can be a problem in permeability reduction, yes.
Can you comment on the experience of tapping into sedimentary reservoirs for high temperature applications, such as when you're tapping a resource that is more than 100 degrees? So what is the difference in say stimulation or utilization methods?
Mm-hmm. Yeah, so first of all, the higher temperatures will cause different problems. So we just talked about microbial activity. This is most abundant between 60 and 80 or 40 and 80 degrees. So you might have less microbial activity, which is a good thing at that time. Regarding mineral precipitation, you also will face different precipitation with different minerals that precipitate, and it more goes into like metals. Might want to look at the publications on the Karlsruhe side, close to Berlin. This is a reservoir that you're just mentioning, above 100 degrees, sedimentary reservoir. And the formation, of course, is much tighter. So this is a problem for, yeah, like an initial problem for porosity permeability, which might be much lower and greater depths at higher temperatures. So it's always a balance of how deep you want to go, how high temperature you want, and the downsides being it's a more tight reservoir. There might be severe precipitation of minerals that then are also not that easy to dissolve again. So metals are not that easy once they precipitate. They really clog up your system compared to shallower systems, lower temperature systems, where you mostly have like hydroxides, iron minerals, sulfate minerals, carbonates that precipitate, and then are probably not sulfates, but the other minerals are easier to dissolve again. To remediate your problem might be easier in these shallower systems.
And then on the Mesobereni case study, have there been other sort of geophysical downhole logging methods done to say confirm the effect of chemical stimulation?
As far as I remember, no, we did not do a big logging campaign afterwards. I need to check the report again, but the most clear effect we saw in the temperature log. So it was the clearest signal that we could get, and that was actually enough for us to prove, because it was so clear also from the injection test afterwards that we increased the injectivity index quite a bit. Yeah.
Maybe just a comment on rig operations when it comes to chemical stimulation. Are there any specific sort of skills or safety practices needed when doing chemical stimulation?
Mm-hmm. Yes, for sure there are. I can't tell you all the details right now. I can look into our reports and what safety measures we took at that time. They are quite kind of regulated, structured. It's somehow easy to follow. The company we hired at the time was very familiar with that, and there was no big issue in following these procedures. But of course, yes. So using HCl means, yeah, not touching the environment, no contact with the environment, no contact with the people working on site. Have as few people as possible on site and close to the fluid also. Make it as automatic as possible, keep far, and then also once you're done with your stimulation, the back flush I think is important, and somehow maybe sometimes overseen or neglected, because the back flush can be quite acidic still, depending on how effective and how deep your stimulation fluid went into the reservoir and was mixed with the reservoir fluid. If it could not, then it will just come back as it was before. So it's still a strong acid. And at that time, I remember we had quite some discussions and thoughts about the backflush tanks and also the disposal of that material that we had to do within the country, and not driving that material too far to avoid any risk of having having accidents or whatever. So you want to have it safe from to the place and also back to a disposal place. And we, at that time, we ordered a few more buffer tanks to be able to store this backflush fluid, which was still acid and will be acid still, more actually than we expected, to just be on the safe side in case there's more backflush from the reservoir, because we probably opened some fluid pathways and some either fractures or porosity areas, porous areas that we didn't expect. So we can still cover that fluid and be safe in that terms.
So maybe just to wrap up the conversation, if there was a geothermal developer was considering to a chemical stimulation for an unproductive or low productivity sedimentary reservoir, what kind of data should they collect, from the most basic data to the most kind of sophisticated data that is possible to ensure success of the stimulation program?
Yeah. Well, I think to the upper end, there's no end. Do as much as you can if you have unlimited time and unlimited budget. For us, it was key to have a safe working environment at the surface, to have enough space to work on site. And then downhole, I think it's key to make sure your well is in good order, as a safe environment to work in. That's why we did this extensive logging in the beginning, to make sure the well is not damaged and is not corroded, is not unstable. That can then cause quite severe problems if you have that and your injection fluid is going somewhere where you didn't want it to go. And yeah, that for sure. So make sure your well at the surface, but also at the subsurface, is in good shape to work in. Then regarding more the data side, I think whatever you can get in terms of well testing is good. Injection tests, lifting tests, production tests. We saw that injectivity and productivity can be quite different in one well. So if you reverse the flow, it can be quite different. So be prepared that a lot of water is coming when you produce, but is not being able to be injected. So testing that before is important, to be prepared then for the operation at surface also, again, like I mentioned, the buffer tanks. And then for us, again, the temperature log was key. So the temperature log in that case helped us a lot. What I always also say is a must is fluid sampling. You need to observe if your fluid is changing, and it's not just to be alerted once it's changing. You can also foresee or even model beforehand, if you have an initial sample, what you might expect to be changed. And then if you see an unexpected change, you might, you can understand that you're probably tapping another part of the reservoir, you're producing another fluid, you're probably connected your system to another aquifer, and so on. So chemistry is such an important tool to understand your reservoir, to understand processes that go on at depth. It's so easy to do. It's a very basic monitoring, and it's very cheap to do. So I always recommend that as well.
Okay then, and that's the time for us. We have a couple of leftover questions, but I'll forward them to Maren, and she'll just get to those at a later time. Thank you for the time. Thank you for doing the presentation.
Well, thank you so much, everyone, for the questions. It was a good discussion.
Okay, thank you everyone for the time, and I wish everyone a happy weekend. Goodbye.
Goodbye.